Then the last talk of this session is by Aslan Askarov. Aslan is an associate professor at Aarhus University, and he's an expert in an area called language-based security. So who better can give a talk about how to read a PL security paper? Go for it, Aslan.
Thank you. Thank you, Marco. Is the sound okay? All right. Hello, everyone. So I want to talk about how to read PL security papers. If you're attending a conference like this, and also other conferences that are in the general area of programming languages, you will see that there are sessions dedicated to security, computer security. If you have just started working in the area of programming languages, you might have seen these textbooks. If you flip through the table of contents of these textbooks, there is no security in there. So how do you survive a session on computer security if you happen to be here? And there is also, so this is to help you. To help me, I submit papers to these conferences. And sometimes, once you get more and more mature, your advisors and your mentors will hand you over the papers to review. You may review my papers, so I want you to have the right mindset when reading my papers. All right. So today I want to equip you with a few questions that you should be asking yourself when you see a paper on computer security in the PL proceedings. These are the questions I use. It's generally a very broad topic, so the usual disclaimer is this is just perspective of one single person, okay? So if you look into a paper in the proceedings, so this is your typical anatomy, right? You will have an introduction over here, you'll have a conclusion, related work, sort of, here you'll get your the meat and potatoes, the Greek letters and the graphs section of your paper. A PL security paper is more or less like this, with the key distinctions is you will see there something called a threat model, right? This is really important. And I cannot underemphasize how important it is, right? But rather than me telling you why this is important, let me bring in a quote by somebody else. This is a very nice write-up from 2012 in CACM, so it's kind of accessible, by David Bazin and Srijan Kapkun, where they are reflecting on the research value of publishing attacks. And the highlighted sentence is the key. They say, what makes security special is the role of the adversary, right? Cue the threat model that I was talking about. A system security can only be evaluated with respect to a model of the adversary, that is description of their capabilities, right? There's one more quote that I really like from this paper, so let me share it with you. So just earlier they say, as our physical and digital worlds become more tightly coupled, the increase of attacks will increase as well as their consequences. You know this stuff, right? You just see it in the news. But this is really nice. They say many of these attacks will be newsworthy, but most will not be research-worthy. So this brings another question. If you're reading a paper, where is the research worthiness of the result that's in the paper? Is it just yet another iteration of the bug that we have known for 40, 50 years, just in another system because people didn't do their homework? And then they conclude here, in our view, the most important reason for studying attacks is that they can help refine this model. Okay, so the adversary. So what's the adversarial thinking? And the adversarial thinking is thinking about abstractions. As PL researchers, as computer scientists in general, as engineers, so to say, we are in the business of building abstractions, right? That's what we do. The adversary's goal is to think in between the abstractions. That's what they're thinking. So if this is your sort of like one way to display cake of the abstractions that we work with, this is a picture from a very nice write-up by Frank Peasons. So this looks familiar, right? Hardware description languages, processor, and so on and so forth. On top of this, we have high-level programming languages. PL is everywhere here, right? Even at the level of a hardware, there is a programming language, right? Let alone at the top level. We use programming languages to operate, to implement the systems. So it's obviously relevant that we see papers on programming languages and security. And you can enumerate a number of instances where there are issues. For instance, the classical ones are about the buffer overflows, where the attacker knows how the memory is laid out, but the programmer doesn't think about it. So the adversary is exploiting really the gap in the abstraction layers. The adversary thinks like this not just in the digital world, they also think about it like this, exploiting the gaps in the physical world. So let me give you just two different examples. So if you have a smartphone, you have a keyboard, you have a desk, you can use the smartphone accelerometer to infer keystrokes from the desk. So, so there's basically, as you type in your password, the accelerometer picks up what's going on, right? So again, really thinking in between abstraction layers. This is my favorite computer security paper, where somebody figured out that the DNA machines that are used out there for DNA sequencing, nobody cares about their computer security, because usually they're kind of like in a lab somewhere. But as a matter of fact, you can synthesize a biological substance that once it's actually being picked up by the DNA sequencer will trigger a sequence of events that will end up in a buffer overflow, right? So, and then it's pretty cute, right? So you can think about, like, this is really the way you can think as an adversary. So the threat model, right? What is really the threat model? The key question here is really simple. Who is the attacker? What can they do? For example, if you have this picture, where are they in this picture? Where are they on the stack? Right? They can be across the network, they can be on the processor, they can be in the cloud with you, and so on and so forth. And all attackers are valid. What's important is that the paper at hand is actually, they know what attacker they have in mind, right? So you have to be aware of it. And sometimes it's meaningful to compare different strengths of the adversary, right? You can say that, oh, I have an attacker who only observes inputs and outputs, and then I have my work focused on this attacker. Good, right? We're clear about the rules of the game. We're defining the rules of the game. So the threat model is really like, what are the rules? Sometimes you can have someone who's stronger. They will not only just observe the I/O, they will also observe all the concurrent I/O, concurrent writes into the memory. For example, if they are running in a parallel process. Or they may have so much access to the machine that they can look into the timing of the events, right? And this relevance of different threat models, it evolves over time in the literature, right? So timing attacks are really focused right now. There's a lot of work, but it's not like community didn't know about them. They've known about them for 20, 30 years. It's just they were not relevant, because in order to perform a timing attack, you would assume that the adversary would have to have physical proximity to the device. These days, they may just be on the cloud sharing the same data center rack with you. So that gives them that possibility. So suddenly an attack that considered to be kind of, you need to have a lot of privilege to exploit it, is becoming something that can be done at scale, right? Once these things can be done at scale, they become relevant. Another example is attacker knowing the source of a program versus providing the program that's going to be executed. And before the browsers, people didn't necessarily take seriously the fact that we can run adversarial code. But we do it all the time in the browser, right? The code comes that's executed from God knows where, right? So it becomes relevant. So the question number one, when I read a paper that's about programming languages and security, is the threat model any good? Do the people writing the paper know what their threat model is? I hope they do, right? And the nice thing about asking this question is it's the threat model that keeps us grounded, right? And they come in all forms, but I think it's important. It's okay if the attacker model, if the threat model is relatively weak, right? So they may assume that, we're just only focusing on the issues where the program at hand is not something that's given to us by someone who is really malicious, but we're just trying to fix incompetence in programmers working, right? That's okay, right? So we can consider a relatively weak threat model, but then the paper better than compensate for it. Maybe they can perform some kind of a static analysis that will target real code, right, for this kind of a threat model. So this is the security fault theorem. I don't really have a citation for it. I just talked to some bunch of colleagues and asked them, does this make sense? And he said, yeah. So in between security, expressivity, and performance, usually you get to choose 2 out of 3, right? And the threat model here kind of helps, right? So you can have relatively good expressivity with relatively good performance, and people doing optimizations already there might start doubt me, but usually security is something that's compromised, right? On the other hand, you can have good performance, good security, but you can't really program anything if you have that system, because then it's going to be extremely restrictive. Okay, make sense? If you have any questions, please shout, right? So that we can make it. Yes?
So I'm a little confused about what a weak attacker means. Is a weak attacker someone? So is a weak attacker someone that does not have a lot of knowledge and then attacks like that? Or is a weak attacker an attacker that can't do a lot of damage?
Right. So a weak attacker, let me give an example. Between an attacker who knows what program you're running, who doesn't know what program you're running, and who has given you the program, the one who has given you the program is the strongest.
Okay.
Right? The one who doesn't know what program you're running is the weakest.
Okay.
Right? Make sense?
Yes.
How can we have security and performance together? My assumption is if we have security checks, we need to give up on the
We
performance.
reject most programs. Because when we sacrifice expressivity.
So we sacrifice
Expressivity. So I will give you, let me give you, so I can tell you, yes, here is a little programming, domain-specific programming language. You can implement, you know, a few algorithms in it, but not much more than that, right? So it's going to be extremely restrictive. A good example of that is the literature on implementing cryptographic primitives. So in the literature on cryptographic primitives, there's a survey in cryptographically aided cryptography. I don't have a quote on it here, but it's like 150 citations, I think, in that paper. Marco might know. The research questions they're asking is, how can we use a low-level programming language, such as assembly or C, to implement cryptographic primitives, such as RSA, and so on and so forth? So they come up with kind of static analysis, restrictions, domain-specific languages, the whole garden variety of everything people talk about here, to target that concrete problem. The programming languages and static analysis they come up with is extremely restrictive. You cannot have an arbitrarily looping construction in that language, right? Because they say, we're implementing crypto, loops have to terminate. Boom, right? So that is an example of then restricted expressivity.
Okay, thanks.
Okay, but you get a relatively high security guarantee because we're talking about cryptographically bounded attackers, so on and so forth. Okay? Good, let's go on. All right. There are subtleties in threat models, right? So pay attention. So usually we will say that security against a strong adversary implies security against a weaker one. Earlier to your question, I gave you an example. Well, if I can show you that my system is secure against an adversary who has given me the code, that's the strongest one, then it's probably going to be also secure against the adversary who has less capabilities. They don't know what I'm running, right? So that kind of common sense. There are caveats, right? There are subtleties. So pay attention. There's a three-liner here. Three-liner, and I have two users. I have A and B. A is the manager. B is the employee. So at the moment of executing the first line of code, manager can know everything professional about their employee. So if I have a line that says, send to A what B's salary is, that's A-okay, right? They have access. It's okay to let them know. Now it's time for A to retire. They are no longer the manager. We are doing the same operation yet again after A has retired. Now we're asking ourselves the question, well, this was okay, fine. What about this one? Is this okay or not? Some of you will say, no, it's not okay because A is no longer the manager, right? They have no business learning this information. Somebody else say, well, that's a very operational way of looking at things. Let's think about what does A actually learn from knowing this, right? So if I knew that, you know, my employee's salary was $100 yesterday, nothing's changed, just by sending this again, I'm not learning anything new. I knew this, right? So you can play it both ways. But the difference here is I am in this case, this is okay if we assume that we have an attacker who can remember everything they have seen. If you have, on the other hand, an attacker who starts forgetting things, who by common sense will also be an attacker who is relatively weaker, then this is actually not okay. So we have this little subtle thing that suddenly this little free liner is okay for a strong attacker, the one who keeps remembering, but not okay for an attacker who is forgetting stuff, right? So there are subtleties. Pay attention to these subtleties. They usually arise when there is some kind of dynamicism in the system. There's dynamicism here because the security specification has changed halfway through. A has retired, right? It's not a static policy. Yes?
Also, guys, like, what if like A salary has changed in between? Sorry,
Let's
B
assume
salary.
yes, that's also a valid question. But assume it did not change, right? Assume we know that the salary changes at the first of the month, right? And we're between 15th and 16th, right? For the sake of example. But yeah, you're perfectly right. Make sense? Shall we go on? Okay. So this was about threat models. So asking the question about what's a threat model is the first technical thing that I want you to keep in mind when you're reading the papers. The second thing that I do is I use this Lampson's notions of elements of security, right? I think it predates Lampson. I've seen this given, he gave a lecture at Maktobedorf a while ago. So it's really these three components. It's about policies, mechanisms, and assurance. And if you're coming to this from a programming languages background, it's specification, it's implementation, and it's soundness, right? So these are the same things. I like to point them in this kind of a diagram. So you have a policy, and the policy is what is the meaning of the security in the first place? That is a very, very, very much a high-level question. The things I expect to see here is confidentiality, preserve the secret, is integrity, preserve the integrity of the system, availability, and so on. These are high-level conceptual notions. The less technical they are, the better, because it's about what is it we want. All the technical complications are in the mechanisms and the assurance. So in the assurance, here we will have your types, your monitors, your static analysis, program verification, fancy runtime systems, and so on. And in the assurance, you will have very complicated proof engineering, right? That's where it is. So this is how we link together. If you haven't seen this, it's very easy to conflate policy and the mechanism. A good example of that is, for example, people sometimes conflate good cryptography with a policy, right? It's a good engineering to do good cryptography. But cryptography is a mechanism to give you the confidentiality. Policy is the confidentiality, right? So keep that in mind. Focus on what's at stake here. Okay. So then the question is, question number 2 when I read the PL security paper, is what are the policy mechanism assurance elements? And question 0 is, does the paper even have a definition of security, right? Do the authors of this paper even understand what they mean by security in this case? Sometimes they don't. Sometimes they say security is just this should not happen, that should not happen, and this should not happen. So that puts it in a bit of an ad hoc situation, right? So these are just things that are not supposed to happen. You don't really have a positive definition of security. Doesn't mean the paper is bad. There may be other good things about the paper. Or it means that the security question at hand is really complicated. So complicated that the state of the art has not yet reached the point where these notions have yet been given a good formal definition, right? That's a symptom of something that is not there. If there is a good security definition, then the next question to ask is, what kind of property is it, right? Things I like in the security policy, I like the security policy that is semantic. For instance, if I'm asking the conceptual question, given a piece of code, is this code secure or not? That should not depend on is there dead code in the source program or not? Make sense? Right? So it should be really semantic, right? It's nice to have a security definition that's focused on on the threat model. It's attacker-centric. And I also like the security definitions to be conceptually shallow. Now, you don't really relate conceptual shallowness with goodness, but a good security definition is something that you can explain to your family member who doesn't know anything about computer security, right? So, and then, again, keep all the complications in the mechanisms and in the assurance, right? We have time for an example. Yes, I think we have time for an example. So I'll give you a little programming language that you will see in a textbook, right? Your classical imperative programming language. And I'll give you 3 different example policies. And the first one will be, well, if I have this programming language, the interesting things about this programming language, so this is just the while that you've seen, I hope you've seen before. And I have primitives for input and output over a channel, and I can have a channel that's secret and public. Okay? Right, that's it. And I can have different kind of security policies here. I can say there shouldn't be any public output after secret inputs. How do I think about this? Well, I can think about, well, if this is my trace, this is my output on a public channel, then there is a secret input, and after this, there shouldn't be anything blue over here, right? That's how I'm thinking about it. You can think about outputs to public channel must be copied to secret channel, right? This is something a little subtler, right? So you can see, well, okay, there's an output here. There must be a bunch of events, but in the end, there's got to be a copy of the same thing, right? So this is, like, you can see, well, the first one looks like a safety property. This one is, the middle one looks like a form of a liveness property, right? So we're starting to make things a little more complicated. This last one says about public output should not depend on the secret input. This is something I cannot express, even formally, I cannot express as a property that takes only one trace into account. I have to reason about all possible traces, right? And this is, so when I say that all possible traces, for all possible traces, this is how I would encode my predicate on the all possible executions, right? This is something that you may have seen in the literature as hyperproperties. Okay, that was number 2. The third way I'm looking into the paper, I'm evaluating it using this classical design principles from Salzer and Schroeder. This is one of my favorite papers. It's from 1975. I read this paper every year because I teach a course on this stuff, and we look into these things. And one of the things they do is they come up with a bunch of design principles that one should adhere to when building a secure systems. And these are, a lot of them are common sense, but it's kind of remarkable how much has they've gotten right more or less 50 years ago, right? Economy of mechanism, your system should be simple because it's easy to verify. If you ever fire to prove a system, you will appreciate the simplicity of things you need to prove, right? So obviously, fail-safe defaults do not give access by default. Makes sense. Complete mediation, do not trade performance for security, makes sense. Open design, no security for obscurity, also makes sense. Separation of privilege. This one escaped me until like half a year ago. I was like thinking, what the hell is this? Can I come up with a good modern example of a separation of privilege? The one they give in the paper is about, well, if you have a system that launches rockets, you need 2 high-level generals, each with their key to sort of fire up the missile, right? So then if one of the general's key is compromised, then you still don't have rockets in the sky, right? So you separate the privilege to perform a security-sensitive operation. And then dawned on me, the most modern incarnation of that is what you will call a multi-factor authentication, right? Where you have to know your password and you have to have a device. It's actually sort of like, it's kind of fascinating that it has this new modern reincarnation. Least privilege, need to know, you may have seen this. Least common mechanism turns out to be incredibly powerful. And then they talk about psychological acceptability, that the passwords are not a good idea in 1975. So please go read that paper. But I want to emphasize why it's important is because, why do I like these principles, is if you have if you exercised and thought about these ideas quite a bit, you realize there's very little new in computer security. Because these principles really, really help you think about the same phenomenon appearing at different levels in your system, right? For example, there's a principle called least common mechanism that says one should minimize the amount of mechanism that's common by more than one user and dependent on by all users, right? Every shared mechanism, especially one involving shared variables, represents a potential information path between users and must be designed with great care. Further, any mechanism serving all users must be certified to the satisfaction of every user. So this is really cool, because this is a principle that keeps on giving. You can design a program analysis that will tell you, well, there's got to be separation that needs to be enforced, or you can design a program analysis that will tell you, well, we're going to allow sharing of resources, but we will prove that that sharing of resources is actually sound, right? And the idea that if you have something that is common in your stack, and that creates a security issue, I mean, that is something that's common for a processor cache, for a disk that shares the vibrations. So it's the same principle that can be exercised across many, many, many layers over. OK. How much time do I have?
Like
1 minute. OK, good. I'll skip some examples. I'll tell you one thing. So privacy. You will see privacy a lot. And my recent revelation is I don't think I understand privacy. I've been doing work in this area for almost 20 years. In security conferences, security and privacy is bundled together. People kind of acknowledge that they are related but not the same. And the more I think about it, the more I realize I don't know anything about privacy. If you know people working in other areas of CS, they will know, well, in information systems, there's a notion of privacy that's about contextual integrity. I have more time? Yeah. OK. In theory, there's a notion of differential privacy, right? So you can go as far as 1890 to the paper by Warren and Brandeis. It's one of my favorite papers as of lately. It has nothing to do with computer science, but it has a lot to do with privacy. And what they do here is they talk about the privacy as the right to be let alone. I encourage you to go and read this paper, because it's just an amazing example of no bullshit writing. You know? So they will, and how far ahead of time it's been. For instance, they say instantaneous photographs and newspaper enterprises have invaded the sacred precincts of private and domestic life. Numerous mechanical devices threaten to make good the prediction that what is whispered in the closet shall be proclaimed from the housetops. I find this very relevant to today, right? And this is a long time ago. And then they kind of predict fake news. They talk about the fact that even gossip apparently harmless when widely and persistently circulated is potent for evil. And my favorite line, it both belittles and perverts, right? Can you write a PLDI paper in which you will, I dare you to write a PLDI paper where you will have it both belittles and perverts. Related to the why don't I understand privacy? So I told you about this idea of the least common mechanism being a sound way of thinking about the systems, that basically, you know, if you, the less sharing there is, the better you are, right? That's kind of the general idea, one way of interpreting that. Well, comes this cute cat theory of censorship. This is by Ethan Zuckerman. The paper is from 13, I've seen. It's been also quoted from 08. And what this cute cat theory of censorship says is that if there is a platform, think of a Facebook and Twitter, so on, and if this is a general purpose platform that's used by people, it's harder to censor it. It's harder to shut it down because people like their cute cats. But that's a platform that can be used for the activism. So if you think about privacy more generally, not just from the perspective of what you see in some of the theory conferences, right? But what is it actually privacy for people? And censorship resilience is one of the aspects of it, right? Then suddenly the thinking principle of designing a system is a challenge, because this is really very much the opposite of what the least common principle tells you, that you should have a separate system for private conversation and a separate system for cute cats, right? So this is why I think it's kind of nice to think about these things. Do I have a time for more? Yes. OK. I'll show you one more technical thing. So you have to be careful about the details, right? So I showed you this least common mechanism. So, and the idea is that as we are implementing systems, we sort of need to be aware of this subtleties. So let me share you a subtlety. So in my group, we have a homegrown little programming language that we call Troop. And the idea is that we basically use it as a research lab to play with different ideas. You don't need to know a lot, but I'll just give you this example. Technical, but stay with me. So what you see here is 3 different processes. So we've got the left one over here. This one has access to the secret. We have a middle one, does not have access to the secret. And then we have the rightmost one. That one doesn't have access to the secret. So we have a parallel composition of 3 processes. Okay? What happens here is that we branch on the secret when we're doing something that's going to take 100 units of time, doesn't matter what. Here we will take 20 units of time, doesn't matter what. Over here, we have just a straight line code. It's going to take 50 units of time, and then we'll perform a side effect. The side effect will consist of writing 1 on the public channel. And here we have just the side effect of writing 0 on the public channel. Okay? So I'm going to tell you, if you consider implementing a scheduler that's actually going to be, implementing this abstraction, right? And the scheduler is round robin. This is A-OK. I implemented the scheduler, right? The first thing, it was A-OK. But, even for a toy language, we itch to add performance, right? So what do you think is the first way to add performance to something like this? You have an idea? Will we add performance? No. Anyone else? Say again? Caching. Okay, so I'll tell you. So what you do is you batch. So instead of sort of interrupting the execution at each instruction, you let each of the processes to run for a little longer, right? And then you make the context switching coarser, right? And that gives you better cache locality, for example, right? Because there's fewer context switching. So that's like the first textbook implementation of making things a little faster when it comes to these things. Okay, so I implemented it, and I have chosen sort of a countdown. So this is n steps per thread, and for this example, let's set it at 60. Okay, so what's going to happen is with each instruction, I'm going to decrease the counter. So it's 60, 59. When it reaches the 0, we context switch. All right? And so on and so forth. So let's do this. So if I start with 60, I'm going to be executing this process. I will run out of my counter, so I will be here somewhere, for instance. So if this takes 1, this will take what? 59, so there will be still 59 instructions. So we will set the counter to 0, right? We will context switch over here. It will be 60 again. This is 51, right? So we will make the public right. We will context switch over here, and then we will make the second public right. So the order of these 2 sends will be 1, 0. Okay? With me? Now, let's suppose that we're executing this again, but now we are in a situation where this is a false branch. So I'm going to come over here. So this is 1. This is 20. So, and I'm done. What's my counter at? 60 minus 21, 39? Yes. My bug was that I did not reset the counter. So it's 39. We're out of things to execute. We're context switching with 39. We will not get to the send, right? The counter will go to 0 in the middle of the skip, right? So then the counter reaches to 0 before reaching the send. The context switch, we do this first, and then we're coming back here, we're doing the second. So that little bug of me forgetting to reset my counter leads to the fact that now the order of the side effects is 0, 1, right? What functional specification would catch that bug? None. You need security specification for these things, right? I didn't know. The only reason I knew about this attack because we kind of predicted that this is something that can happen. And then I did property-based testing of my implementation to see is it actually possible. And I was really surprised that I had my own bug in my own code. OK. My chair is signaling that I should wrap up. And I think I'm ready to wrap up. So I shared with you the thinking process I have when reading a PL security paper. This is just the summary of these things. You have to remember what the threat model is. You keep the security policy mechanism assurance triangle in check. That really helps you to position the paper. And appreciate that a lot of the PL techniques are in the mechanisms and in the proof techniques, right? And then think if you can relate what the paper is doing at a high level to this 75 paper from the 75 on by Salter and Schroeder on the design principles. And these questions are there to assist your core expertise, right? So whatever it is your core expertise, that will be, you know, an extra booster to make your way through the paper. If you are a PL generalist, you don't care about security, I think there is a lot of value in reading these papers because, again, security by itself is an incredibly pragmatic discipline, right? The discussion about threat models is there to tell you that even though these papers may be theoretical, they are really grounded in practice, right? So it gives you touch with realism, if you will. And if you are expert in something, chances are your expertise will be relevant. If you're expert in program analysis, you might have an application, and so on and so forth. Garbage collection, proof engineering. Chances are there will be applications for your core expertise in security. A slide with a few reading takeaways. These are sort of like survey classic papers, but I want to summarize. Remember that security is about the whole stack. Programming languages are part of implementing the stack, a part of the stack, and I think we will see more of PL security papers in our proceedings. Thank you.
Do we have one quick question?
So, thank you for the talk. My question is that when we consider these different threat models, and what I wonder when I read a paper, that a solution for a threat model, whether it introduces another security, possibility of another security violations or not. Is it something possible?
So let me see if I understand. So the question is, are we introducing insecurities by trying to focus on the security? I can't say it's impossible, right? I can't think of an example from the top of my head, but I wouldn't say it's impossible, right? So because, for example, I don't know, you might make it easier for a stronger attacker to do something, but if that's an attacker that's out of the scope of the paper, that might be sort of technically within the rules that they set up for themselves. Okay. Right.
Thanks.
Other questions?
We had questions during the talk. That's okay.
That's fine.
That's fine.
Then let's thank Aslan again.